Welcome to The Explainer. Today, we're going to tackle something truly mind-bending, the world of quantum computing. We're going to break down how these amazing machines work, right from the ground up, starting with their most fundamental piece.
All right, so to really get this, we got to start with something we all know, the classical bit. I mean, this is the bedrock of everything digital in our lives, from the text you just sent to the movie you're streaming. And right here, you see the huge leap we're about to take. Your classical bit? Think of it like a light switch. It's either on or it's off. Simple. A qubit, though, that's a whole different ballgame. It's more like a coin spinning through the air. Before it lands, is it heads or tails? Well, it's kind of both at the same time. So this totally wild idea has a name, superposition. And let's be super clear here. It's not that we just don't know what state the qubit is in. It's that it literally exists in both states at the exact same time. And this right here, this is the first major key to understanding why quantum computers are so unbelievably powerful.
Okay, so how do you even picture something like that? Well, physicists have a tool for it called the Bloch Sphere. Just imagine a globe. A regular old computer bit can only be at the very top, the North Pole, let's call that 0, or the very bottom, the South Pole, which is 1. That's it. But a qubit, oh man, a qubit can be anywhere on the entire surface of that globe. Every single point represents a different mix, a unique superposition of 0 and 1.
Okay, so one qubit being in two places at once is weird, right? But now, let's see what happens when you start putting them together. This is where things get truly exponential and the real power starts to show.
Think about it with regular computers. If you have 4 classical bits, they can only represent one specific number out of 16 possible combinations at any given time. Like say 1011. It's stuck there. That's all it can be in that moment. But what if you have 4 qubits and each one is in that superposition state we just talked about? Well, that limitation of being stuck in one state, it just goes away. And bam, this is what we call quantum parallelism. That system isn't just holding one of the 16 values, it's holding all 16 of them simultaneously at the same time. You can see how this starts to scale up like crazy, right? And when I say it scales up like crazy, I mean it. Check this out. With just 300 qubits, you can represent more states at the same time than there are atoms in the entire observable universe. Just let that sink in. It's a number so big, it's basically meaningless to us. This is the kind of power that could let us design new drugs, create new materials, solve problems that our biggest, baddest supercomputers today wouldn't even know where to start. Okay, but here's the catch, and it's a big one. We can't actually peek in and see all those states at once. The moment we try to measure a qubit, the magic is over. The act of looking at it forces the qubit to pick one. It collapses down into a plain old 0 or a 1, and the whole superposition vanishes.
So just when you thought things couldn't get any stranger than superposition, well, they do. Let's talk about what happens when you link qubits together in a special way. It's a process called entanglement, and they become so connected that they're basically one single entity. This connection is so weird, so counterintuitive, that it famously drove Albert Einstein crazy. He just couldn't accept it. He called it spooky action at a distance and spent years trying to poke holes in the theory. But guess what? He was wrong. Every experiment has shown that it's absolutely real. Here's an analogy. Imagine you have 2 of those magic coins, and they're entangled. You give one to a friend who goes to Mars. You stay on Earth. If you flip your coin and it lands on heads, you know instantly that your friend's coin on Mars also landed on heads. The information seems to travel faster than the speed of light, and their fates are forever linked.
Okay, so that raises a pretty big question, right? If looking at a qubit ruins the whole thing, how in the world do you actually compute with it? Well, you don't look. You manipulate. You nudge and guide the qubits using a very special set of tools called quantum gates. It's just like how regular computers use logic gates like and, or, and not. Quantum computers have their own set. In the real world, these gates are actually things like super precise laser bursts or microwave pulses that change the qubit state. You have things like the Hadamard gate, which is like your starter pistol for creating superposition, or the X gate, which is basically a quantum version of a NOT gate. It just flips the qubit from 0 to 1.
And here's where it gets cool. You can combine these gates to do really powerful things. For example, you can create that spooky entanglement we were just talking about with a really simple recipe. You just need one Hadamard gate and one CNOT gate.
You apply them in the right order, and boom, your two qubits are now entangled. So this all sounds amazing, right? Almost like science fiction. But bringing it into the real world, well, that comes with a massive, massive challenge. Which leads to the obvious question. If this is so powerful, why don't we have quantum laptops yet? What's the one big thing holding everything back? Well, the number one enemy, the main villain in this whole story, is something called decoherence. It's this constant, nagging process where the outside world leaks in and destroys those delicate quantum states we need, basically turning our super powerful qubits back into boring old regular bits.
I love this analogy. Think of a qubit in superposition like the most delicate soap bubble you could imagine. Literally anything can pop it. A tiny bit of heat, the smallest vibration, a stray radio wave, even a particle from outer space. Poof, it's gone.
And to fight this, scientists have to go to some pretty insane lengths. They build these giant, crazy-looking refrigerators, you've probably seen pictures of them, all to cool the quantum chips down to temperatures just a tiny fraction of a degree above absolute zero. We're talking hundreds of times colder than deep space. And that right there really sums up the whole challenge. The race today isn't just about cramming more and more qubits onto a chip. It's about building better, more stable qubits, and creating environments so perfectly isolated from the universe that these fragile states can survive long enough to actually do some useful work.
So we've gone from a simple on-off switch to a spinning coin holding countless possibilities. We've seen its almost unimaginable power, but also its incredible fragility. It leaves you wondering, if we can finally tame these quantum effects, if we can learn to control them, what problems that we think are impossible today could we finally solve?